In this part of the course Chemistry 2, we are going to solve the first exercise of the third worksheet. In this exercise, we have a sample of a perfect gas that is initially at this state, and it will undergo a thermodynamic cycle that is made up of three reversible processes. We have the isothermal change, isobaric change, and isochoric change and isobaric change. First, we have to draw the cycle PV diagram, and we'll calculate all these thermodynamic properties. Also, we'll discuss the law of thermodynamics if it is verified through this cycle. So first, we have the perfect gas that is in state A. We have the pressure in A and temperature in state A. Here it is equal to 0.5 atmosphere, and temperature it is 1000 Kelvin. The volume A is not given yet. So now this 1 mole of perfect gas will undergo first an isothermal change to a state B, where the final pressure is equal to 2 atm. Here we have isothermal, which means that temperature is constant. So the pressure has increased to a value of 2 atm. Because it is isothermal, therefore the temperature in state B is equal to temperature in state A, which is equal to 1000 Kelvin. And the volume B is not given. So here the first change. After that, here it is the state B. After that, the gas undergo an isochoric change, which means that the volume remains constant. And here the pressure, they say that the pressure is equal to the pressure in state A. So we have the pressure in state C is equal to 0.5 atm. And because it is an isochoric change, therefore the volume in state C is equal to the volume in state B, which is not yet determined. And here the temperature is not given also. And after that, the gas returns to its initial state through an isobaric change, which means that the pressure remains constant. Now, before to draw the PV diagram, it's better to calculate each state variable. So we start by the state A. Here we have P and temperature are given, so only the volume is not known. So we can determine the volume through the equation of the perfect gas. PV is equal to nRT. Therefore, the volume in state A is equal to N times R times T in state A over P in state A. So we replace each variable by its value. Here we have 1 times 0.082 times 1000 Kelvin over the pressure here, which is equal to 0.5. Here we have used the R, the constant gas, which is 0.082, because we have here the pressure in atm. So we must use this constant because it is in liter atmosphere over Kelvin mole. When we use the other constant, which is 831, which is in joule Kelvin mole, we must use the pressure in Pascal. So here it's better to use this constant instead of the R that is given in joule per Kelvin per mole. And here we get a value of 164 liters, So here is the volume in state A. So we add this value later. Now we can calculate also the volume in state B with the same equation. So here we have the volume in state B is equal to nRT in state B over P in state B. Here we have 1 times 0.82 times 1000 Kelvin, but here we have 2 atm, and we get a value of 41 liters. So here we have 41 liters. We remark that the volume has decreased and the pressure has increased, which means that we have a compression process. Now, because from the state B to the state C, it is an isochoric change, therefore the volume in state C is equal to 41 liters, and here the temperature will be determined through this equation, the perfect gas equation. So the temperature in state C is equal to the pressure times volume in state C over N times R. So we replace each variable. We have 0.5 times 41 over 1 times 0.082. Here again we use the R constant because the pressure is in atm. And if we plug each value in a calculator, we get a temperature of 250 Kelvin. So here we have 250 Kelvin. Now all the state variables are calculated. Now we can draw the PV diagram. Here it is. So P against V. We have in state A the pressure is at its highest level, which is 164 liters, and the pressure it is at its lowest value, which is 0.5 atm. So the state A is spotted here. Now the change from A to B, it is isothermal, and the pressure we said that it has increased to a value of 2 atm, and the volume has decreased to a value of 41 liters. So here is the state B. It is an isothermal change where temperature is constant. After that, from B to a state C, it is an isochoric change, as we have here. Isochoric change, which means that the volume remains the same and the pressure has decreased to a value of 0.5 atm. Here it is. So here we have this state C. Here's the second change, and the third change, from state C the gas returns to its initial state. So here is the thermodynamic cycles. We have 3 steps, 1, 2, and 3. So now we have to determine the thermodynamic properties for each process. We start by the first one, which is isothermal, from A to B. So we start first by the determination of the work. The work is equal to the integral to P dV. And because it is an isothermal change and the pressure is not constant, so we'll replace P by these variables, because it is a perfect gas. So we can write minus nRT V dV. Now N and R and T are constant, so they can be removed from the integral. dV over V. From the initial state to the final state. And here is the expression of the work when the process is isothermal. Normal logarithm volume in state B over the volume in initial state. Now we just replace each variable by its value, which is equal to 1 times, but in this case we will use the R in joule, times temperature, which is equal to 1000 Kelvin, times the logarithm of the final volume in state B is equal to 41 liters over 164 liters. And we get a value of 11,500 joules, but it's better to use the kilojoules. So we'll convert to kilojoules because 1 joule is equal to 10 to the power of minus 3 kilojoules. So here is the conversion factor. And we have this value for the work in kilojoules. And for all the other thermodynamic properties, we'll use the kilojoule as unit. Now for the heat of the change from A to B, it will be determined. But before, because it is isothermal and we know that the internal energy is a function only of the temperature. If the temperature remains unchanged, which means that the change in internal enthalpy is 0. And also from the first law of thermodynamics, we know that the change in internal energy is related to the sum of the heat and the work. And therefore, the value of heat is equal, when it is isothermal, to negative work, which is equal to minus 11.5 kilojoules. And the value of the internal energy for an isothermal change is equal to 0, because the change in internal energy is function of only temperature, and the same thing with the change in enthalpy. Both are equal to 0. Now it is better to draw a table and to fill for each step. So here we have the first step in kilojoules, the second steps in kilojoules, and the third step, or the third change, also in kilojoule. Here we have the work, the heat, the change in internal energy, and the change in enthalpy. We'll add a fourth column, which is the column of the sum of all these functions. We call it sigma, that will be given in kilojoules. So the first column can be filled because we have calculated the work of the first process, which is equal to 11.5 kilojoules. The work or the heat is negative 11.5, and here we have 0 and 0. Now let's move on to the second process, when the change is isochoric. We have a volume that is constant. When the volume doesn't change, it means that the work which depends on the change in volume is equal to 0. And the heat of the change is equal to Nc sub V delta T. But we must calculate the C sub V, the heat capacity, the molar heat capacity. We know that gamma is equal to Cp over C sub V, which is equal to 1.4. And also we have a second relationship, which says that Cp minus C sub V is equal to R. So we'll replace the value of Cp from this relation. Therefore, we can here we have gamma CV is equal to Cp. So we can replace here C sub V, gamma minus C sub V is equal to R, and C sub V is equal to R over gamma minus 1. Here R is given in 131 in Joule, Kelvin mole. And by replacing each variable by its value, we get a value of 20.8 Joule, Kelvin minus 1, mole minus 1. And the molar heat capacity when the pressure is constant for Cp is equal to gamma Cv, and it is equal to 29.1 Joule, Kelvin minus 1, mole minus 1. So we can replace here 1 times 20.8 times here the temperature, the final temperature. Here we have T in state B or T in state C minus T in state B. Here we have 250 minus 1000 Kelvin. So it will be a negative value because here the final temperature is less than the initial temperature. By plugging each value in a calculator, we get the heat which is equal to a value of minus 15.6 kilojoules. And the change in internal energy is equal to W plus Q, but it is here 0, therefore it will be equal also to minus 15.6 kilojoules. The change in enthalpy is equal to N C sub P delta T. So we use, in this case, this heat capacity, which is equal to 1 times 29.1 times 250 minus 1000 Kelvin. Here, the same thing, it will be negative because we have the final temperature is less than the initial temperature, which is equal to a value of minus 21.8 kilojoules. So there are these values. So we can fill the second column of the table. Here we have work 0, the heat is minus 15.6 kilojoule, the change in internal enthalpy or energy, the same thing, minus 15.6, and the change in enthalpy is equal to minus 21.8 kilojoule. Now let's move on to the third process and the last one, when the change is isobaric. Here the work that is done is equal to minus P delta V, which is equal to minus 0.5 times. Here we have the final volume is for state A and initial volume in state C, which is equal to 164 minus 41. But here we should be careful because here the pressure is in atm, atmosphere, and here in liter, and we are working with unit in joules, so it's better to convert to the joules or kilojoule, because 1 atm times liter is equal to 1.01325 joules, or it is equal to 0.101325 kilojoules. So we have to multiply by this conversion factor. 1 atm liters, here in numerator we have 0.01325 kilojoules. So we can cancel both unit and we get at the end work in kilojoules. So by plugging all these values in calculator, we get a work that is equal to minus 6.23 kilojoules. Now for the heat exchange during this process, it has this expression NCP delta T. Here we replace for each variable 1 times 29.1 times, here we have 1000 Kelvin minus 250 Kelvin. And here we get a value of 21.8 kilojoules. And for the change in internal energy is equal to the sum of work plus heat, which is equal to minus 6.23 plus 21 plus 8. And the change in internal energy is equal to 15.6 kilojoules. And the change in enthalpy, because it is isobaric, so it will be the same as the heat exchange, which is equal to 21.8 kilojoules. Now we can fill the last column. So here we have minus 6.23 and 21.8. Here we have 15.6, and the change in enthalpy is the same as the heat, 21.8. Now we have to verify the first law of thermodynamics. Here, because it is a reversible thermodynamic cycle, so therefore the cyclic work must be not equal to 0, and the same thing here, because they are not state function. But the cyclic work is equal to the cyclic work, but in opposite sign. So if we add 11.5 minus 6.3, we get a value of about 5.3 kilojoules. And here it must be the same, but in opposite sign. If we add this 3 value, also we get 5.3. So this equation is verified. And also, because delta U is a state function, both they are state functions, it means that the sum of all the cyclic internal energy is equal to 0. It must be 0 because it is equal to the cyclic work plus the cyclic heat. So here, if we move through the column, it will get 0, and the same thing if we move through the horizontal table or this line, it will be also 0, and the same thing here. So we can see that the first law of thermodynamics is verified for this reversible cycle.